Hello friends, in this video we will talk about the next asymptotic notation, which is nothing but big O notation, and it's noted by this particular symbol, which is nothing but capital O. Okay, so if you try to compare this particular notation with our previous notation, which is nothing but theta notation, then you can notice that this particular line, right, is missing. So that means here this particular function is not bounded by above and below by constant multipliers of g, but it's bounded by just by above, right? So therefore this is also known as tight upper bound on any function. So now whenever we try to show that one particular function belongs to, let's say, big O of g of n, at the time we just need to find out two constants. One is c and second is n naught. So instead of finding out c1, c2 and n naught, here we just need to find out c and n naught such that this particular relation 0 is less than or equal to f of n less than or equal to c times u of n, this particular relation is true. So that, in other words, after certain point, let's say after n naught, my function cannot get values more than c times u of n, right? So let's say for one particular function, if I say this particular function belongs to big O of n square, so what is the meaning of this particular statement? This means in the worst case, so basically this particular notation is corresponding to worst case analysis, and it will say that in the worst case also the algorithm will not do more than n square number of mathematical operations or n square number of, let's say, comparisons, if it's corresponding to some sorting algorithm, right? And one more thing which is interesting with respect to this particular notation is that this particular result is applicable to all inputs. Okay, so we'll talk about this more afterwards, but the idea is, consider any input for the algorithm. For that particular input, the number of comparisons or number of mathematical operations will be always less than whatever the value of that particular gn function. In this particular case it's n square. So consider any possible input of size n, let's say, your number of comparisons or number of mathematical operations will be less than constant multiplier of n square. So now let me take one example. So let's say my function is like this. Let's say 3n cube plus 5n plus, let's say, 7. So now here I just need to find out values of n naught and c. So this particular function is less than or equal to 3 plus 5 plus 7. So this is similar to our previous method. Since n cube is greater than n raised to 1 and n cube is greater than n raised to 0, we can write like this, and this is nothing but 8 plus 7, which is nothing but 15 n cube. So I can say that value of c is 15, and this is true for all the values which are greater than 1, right? So n naught is 1 and c is 15. For this particular values of c and n naught, this relation is 2. So we can say that this particular function fa of n belongs to big O of n cube, right? So now if we try to consider our previous examples, then we can say that this particular function 5 plus 1 by n, this particular function belongs to big O of 1, and all you need to do is just focus on this part of the analysis, right? And whatever value we get for c2, that is nothing but our c. So c is equal to 6 and n naught is equal to 2, and hence we can say that this particular function belongs to big O of 1. Similarly, this particular polynomial function is in class big O of n raised to k, right? You can verify this. And this particular function 6n log n plus 7n plus 5, it belongs to big O of n log n. And this particular function is in big O of n cube. and this function belongs to big O of n cube.